Hello, my name is Rob Reynolds. Welcome to Calculus Section 5.3. Today we're learning the fundamental theorem of calculus, and it's really not as bad as that sounds, but it is very important. Let me recap some things that we learned in, way back in Chapter 2 and 3, taking the derivatives of 5x cubed gives us 15x squared. So then in Chapter 5, we learned that you could undo, or the antiderivative of 15x squared. Well, instead of decreasing the 3 to a 2, you increase the 2 to a 3, and instead of multiplying the 3 times 5, we're going to divide by that. So it's 15 divided by whatever exponent you increased it to. Of course, that gets you back to the original problem. So I just wanted to recap how to integrate. That's a skill that you're going to need in Section 5.3. But fundamental theorem of calculus helps us find the area underneath the exact area without using Riemann sums and approximations like we did in Section 5.1 and 5.2. Now we can find the exact area underneath the curve using integration. So remember, you have a formula sheet for a lot of 5.1 and 5.2 that you're going to be using, but in 5.3 I don't think we're going to need the formula sheet. We're actually just going to be integrating over these intervals from A to B, or we could go from A to C. And remember, when you integrate, we end up with positive and negative or net area, unless they ask us for the absolute value. So our first example says to find the area at 3. So I'm going to use this yellow formula. I'm going to integrate from -1 to 3 of f at t dt, which says just look at the area between -1 and 3, and it looks like it's 27. Then for f at 3, I'm running out of space, but here, f at 3 says use the blue formula. So I'm going to integrate from 3 to 3 of this function, and of course, that's not moving anywhere from 3 to 3. There's no area underneath the curve, so it's 0. Then in part B, I got to find a sub 5 and f at 5. So the a sub 5 goes back to the yellow. I'm going to integrate from -1 to 5 of the function, and that would give me 3 minus 27, or -24. And the blue function, I'm integrating from 3 to 5, and moving from 3 to 5 gives me the area of 3. And lastly, in part C, I need to find a sub 9 and f at 9. So the yellow function is going from -1 to 9. And again, I get positive area and negative area. So -27 plus 3 minus 35 is -59. And f at 9 is integrating. And from 3 to 9, and that would give me a 3 minus 35, which is -32. Remembering you have positive area here of 3, and then negative area here of 35. Here's the author's explanation of that slide. Of course, you can find all these notes on Blackboard. I hope you've gone and printed off a blank copy of the PDF and you're trying these as I'm explaining them on the video. So for part A, again, we have integration from this function from 2 to 2, and of course we know that that's just 0. So I'm not moving anywhere on this function. Oops, there's no equal sign here, of course. dt, and of course that's 0. Part A. Part B, it says a sub 5, which is, well, I don't know, maybe I should use some geometry here because they say it's a trapezoid. They give me a formula, so I'll do it both methods here. 1/2 the base, let's do 1/2 the height times base 1 plus base 2. A little bit different notation than what they're using, but it means the same thing. So the height of this thing, you may think this is the height, but the bases have to be parallel. So I'm going to use this for base 1 and base 2. would be over here. And then oddly enough, this distance here would be the height. And it says a sub 5, so I know this x is a 5, and so that height distance would be 3. Between 2 and 5 is 3 units. Well, 3, 4, there it is. So 1, 2, 3. Good grief, made a big deal about nothing. So then how do I find this guy right here? Well, that's f at 2, and this is f at 5. So go to the function and evaluate. F at 2 is 7, and f at 5 is 13, and number crunch it, and we get the area of 30. Part C. So, oh, by the way, I could do that through my integration techniques. So from 2 to 5 of 2t plus 3, if I didn't use geometry, which it kind of looks like they wanted me to use, because they kept mentioning the area of a trapezoid, but it never specifically said use geometry. So if I use the techniques of integration, to find the area between 2 and 5, I would increase this 1 to a 2, divide by it, 2 divided by 2 goes to 1, plus 3t, and then evaluate that from 2 to 5. And then the fundamental theorem of calculus, which I just jumped ahead a little bit, says f of b minus f of a. So I don't think I'm supposed to be teaching this yet, but it's going to be coming here. So evaluate the function at 5. So 5 squared plus 15. So I'm plugging this 5 in here. So, well, I don't know how to squeeze it in here. 5 squared plus 15 minus 2 squared plus 6. And I got that by plugging the 2 in to the function. And of course, that's 40 minus 10, and 40 minus 10 still gives me 30. So I'm fairly certain we're supposed to have used this because we haven't introduced the fundamental theorem of calculus yet, but we'll get there. So in part C, it says just find the general equation. If you don't know that it's a 5, let's just say it's a sub x. So I'm going to do the same thing, 1/2. I don't know if that's a 3 anymore, but the way that I found that distance was just 5 minus 2, but in this case it's going to be x minus 2 for the height. This is still going to be 7, which I can evaluate, but this is just f at x. I don't know what that is. So I'm just going to leave that to be the function, 2x plus 3. Yes, the function. So this is just f of x right here at that point. 2x plus 3. So in general, if I didn't know the value of x, I just leave it in terms of x. Well, I'll multiply this out, combining like terms and foiling. I think I'm going to take half of this guy in here. So I'll just get x minus 2 and x plus 5, and I get a function. A sub x is equal to x squared plus 3x minus 10. The neat thing about that function is if I evaluate it at a sub 5, sure enough, I get the same answer, 30. And if I take the derivative of that function, this guy, take the derivative of this, I'll get 2x plus 3, which is the same as my original function. So again, they're trying to explain why the fundamental theorem of calculus is working and all the relationships between derivatives and integrals. So here's the author's explanation of that. So the fundamental theorem of calculus says the explanation that I just kind of went through, it's not an accident. There's neat little relationships here between derivatives and integrals and area underneath the curves. And basically, the derivative and the integral, just like addition undoes subtraction, they kind of undo each other. And you kind of just end up with the function. So it's the derivative and it's the antiderivative. So here, the fundamental theorem of calculus, finally, you get it. we can start using it now. Basically says f of b minus f of a, and then we're going to evaluate the function. So f of b minus f of a is the fundamental theorem of calculus. Finds the area underneath the curve after integration. If I'm ever taking the derivative of the integral, you may think, well, how come this 1 or this 2 that, well, this a term, remember you integrate from a to b, doesn't really matter, and it doesn't really matter what that a term is because to find how fast you're traveling, a car is traveling, the start value is kind of irrelevant. So this is going to bug students where I'm not going to really pay much attention to this a value down here. When I'm taking the derivative of an integral, I'm really just interested in this up here. I'll show you some examples of that in a minute. So let's look at example 3 together. Let's actually integrate this. So integral, I'm going to increase and divide by a 2. 60 divided by 2 is the 30. And then I'm going to integrate this minus 2x cubed, evaluate it between 0 and 10, and do the fundamental theorem of calculus. F of 10 minus f of 0, and f of 10 is going to be 3,000 minus 2,000 minus the f of 0 is just 0, and the final answer is 1,000. So the integral of sine, remember I can pop out the constant, the integral of sine is negative cosine. And you're going to say, well, I thought it was just positive cosine. Well, the derivative of sine is positive cosine, but when I integrate, I got to think about what about the derivative of cosine? Well, that's negative sine, but I'm going the opposite direction, so that's why I throw a negative out in front. So let's evaluate that between 0 and 2 pi. I would recommend just popping out the 3, so it's really the cosine of 2 pi minus the cosine of 0, and of course you need to know unit circle. So this is negative 3, and unit circle would be the cosine would be 1 minus 1 because I'm in the same position, and of course that's negative 3 times 0 or just 0. This last one, we don't know how to do integration with a quotient. There is no low d high minus high d low like we do for products. So I'm going to change this to exponents and try to simplify by integrating t to the negative 1/2 minus, well, I could do t to the negative first, but do you remember the derivative? What can I take the derivative of to get a 1 over t? And I think that's the ln of t. So if I kind of think about going backwards, the derivative of this gives me this. And then over here, I'm going to do integration, which means increase. So this becomes t to the 1/2 because I increase this negative 1/2 by 1. It's positive. And then I divide by the 1/2, which is like multiplying by a 2. And then I do the fundamental theorem of calculus and evaluate that from 1/16 to 1/4. So f of 1/4 minus f of 1/16 does not look fun to me. Let's see if we can grab it together. So 2 times 1/4 to the 1/2 minus the ln of 1/4 is the f of b minus the f of a is 2 times 1/16. I know what some of you are going to do. You're just going to go to your calculators, punch it, and then you're going to think that I don't care about this work, but I do. If you just give me a decimal approximation, I may not give you full credit on your test. So let's see if we can just work this out. This to the 1/2 means the square root of 1/4, which is 2 times 1/2, which is just 1, minus the ln of 1/4. This is the square root of 16, so 2 times 1/4 is 1/2. I'll distribute this negative here, make this a plus, the ln of 1/16. Again, I could pick up my calculator anytime and go decimal, but let's see if I can just continue combining like terms. 1 minus 1/2 is 1/2. And so I'm going to look at this, explore these logs just a little bit. So negative ln of 1/4 plus the ln of 1/16 would really be 4 to the negative first plus the ln of 4 to the negative second. Using log properties, I can dump this down out front. So this is the ln of 4 minus 2 ln of 4s, and that gives me a negative ln 4. So that yellow simplifies. So that would be something that I'd be interested in you demonstrating content knowledge, opposed to just picking up a calculator, which I suppose you've done already. I'm less interested in this decimal answer, more interested in you demonstrating some log properties. Good problem. Here's the author explanation of this. Of course, this is posted on Blackboard, so you're welcome to read through this. Was there another? Oh, so that was example 1, example 2. Here's the author's explanation of, yeah, they got the same thing. So again, I'm a little bit more interested in this exact answer opposed to the decimal approximation. Of course, you could always just pick up your calculator. I've shown you how to do that, the cheat method. So again, your goal is to demonstrate your mathematics. But number 4 looks like it's kind of making a distinction between net area, which is, the integral will do net area because it will do positive plus negative. But then I need to worry about area. Either I use geometry or I could still use integration. I just have to make sure that area is it's always positive area, and I can do that by just taking the absolute value of the function. So when I integrate, I just remember to make sure areas are positive. Well, let me show you what I mean. I'm going to take this function, sheath. Can I multiply that up for you? I think it'll be easier for me to integrate because I don't know the integral of a times b times c. So I'll multiply that out. First of all, using my multiply, stack, and add techniques I've learned from algebra 2. And then I'll integrate, which means increase. That's 3 to a 4. Divide by it, 6/4 is 3/2 minus 2x cubed, if I continue, minus 6x squared. And the fundamental theorem of calculus says evaluate it from f at 2 minus f at negative 1. Well, when I say show the work, I don't really need the number crunching work here, so you could actually just type this in. I would not expect you to show me the number crunching here. So I'll just show you what I do expect of you. At least show me the fundamental theorem of calculus by doing f of b minus f of a. So I'm just going to type this function in to the calculator and then hit trace 2, enter, and get the negative 16 minus the negative 1 is negative 2.5. And I can even go to my calculator and just negative 16 plus 2.5 and math, enter if I want to get negative 27/2. So again, I'm still demonstrating content knowledge by doing the f of b minus f of a. I'm not doing this on my calculator. If you hit math 9, and of course you can do this, but this is not what I'm testing you over. So again, I'll show you what I'm not interested, or you need to convince me that you're not doing this by showing me a little bit more work. X dx, and sure enough, I get the negative 13.5, same as before. So I'm not as interested in that because you didn't do the fundamental theorem of calculus. You're just using your calculator to find an answer, which is a great checking mechanism. But again, I'd really like to see the fundamental theorem of calculus here. So if we change this to just area, everything is the same. it's just down here in part B, I would get the absolute value. I take that back. Let's see. I need to find out where the positives and where the negatives are. So maybe I should graph this real quick. I think I have it graphed. Let's see. Zoom 6. So there was the graph. And then if I'm looking between -1 and 2, I can see it comes from down here. Oh, no. Wait. I'm so sorry. The function was this. I don't want to look at this guy. This is not the function. Well, yeah, that was the function. Oh, I confuzzled myself. Okay, so but what I had in here was this guy. I got to clear out this because I had this guy. Oh, shoot. I had this guy. This blue guy is not the function. That was the integral of it. I need to actually type in the actual function here. Sorry about that. Well, maybe it's comforting to know that I make mistakes too. Too bad I videoed it for the world to see. So zoom, there's a little bit better. So I want to see trace -1, enter. There you go. So I've got some positive area, I've got some negative area. So from trace going to 2. All right, so I think I have a little bit of a view of what this looks like roughly. It looks something like this and then this. So I have some positive area and I have some negative area, and I'm interested in where these things are zeros. I can see right here 6x equals 0 when x equals 0, x equals -1, just finding the roots, and then x equals 2. So -1, 0, and 2 are my zeros, and the green is already positive. So when I integrate from -1 to 0, that's already positive. And I have to go back to the 3/2 x to the 4th. Oh, why did I delete that from my calculator? I'll never know because I need to get that typed back in. And then I need to integrate from 0 to 2 of that same thing. We'll just call that f of x. But I'd go back to my calculator, punch this in, and then do f of 0 minus f of -1. And again, demonstrate the fundamental theorem of calculus, but for sake of time, 5/2. Then this will turn out to be negative, but I'll take the absolute value of that. When I do the fundamental theorem of calculus, and that's -16, and then 16 and the 5/2 turns out to be 37/2. So again, different because I am taking this black negative area and flipping it over and making it actually positive. So it's actually kind of looking like this, and then finding positive area. I hope that made sense to you. But again, show me a little bit of work. Here's the author's explanation of making this a positive area. So again, I want to talk to you in the video with how this undoes, the derivative undoes the integral, and this start value is really kind of irrelevant. So all we need to do is just replace this x or this t with the x, and this answer is sine squared x, and we're done. So if it's backwards, then remember I can say the negative of the derivative of the integral from 5 to x of this function, and then I just ignore the 5 again. This undoes each other, the derivative, and then I have a negative floating around there, and then I just replace x with the t. And again, if you wanted to play around and actually do the fundamental theorem of calculus and do f of b minus f of a and see that that 5 is irrelevant, go for it. It will cancel out for you. But I don't have time on this video to do that. So again, you just have to make sure that it's in the correct form, and this is not in the correct form. I need it from, well, depending on whether that x squared is positive or negative, it could be in the right form, but I don't like that x squared. I'm going to go for a u sub, and I'm going to say let's let u equal x squared. So then remember, whenever you have a u or a u sub for the chain rule, I end up with a du. So I'm going to rewrite this du from 0 to u of the cosine of t squared du. But remember, you're going to end up with a 2x out there because that's my du. Du is the 2x. So that du is my 2x. So this guy becomes, the derivative undoes the integral, just the cosine of u squared, and then I already explained the du is the 2x, and I'm kind of mixing variables here because I can't have a u and an x, so I'll just replace that u back with the cosine of x squared, and I'll throw a, well, remember the u, this u is x squared, and so I need to square the x squared term. So I think I'm going to end up with the cosine of x to the fourth, and I'm just going to throw that 2x out front. So again, that was a little bit harder, but I just wanted to demonstrate this is the chain rule for integration. I hope this video was helpful. If you have questions, feel free to email me. Again, author has solutions, and I have these posted on Blackboard, and you can go through and actually do a lot of your homework with your calculator. But remember, on the test, I'd like to see the worked out solutions. You got to convince me that you're not just punching numbers into a calculator. So if you have questions, please shoot me some emails. You can do number 6 and 7, hopefully on your own. Good luck.